Hi, welcome to Tech Talk with Hughes Performance. I'm Pete Nichols. Today's episode's pretty exciting. It might be one that you've all been waiting for, and we're going to answer the question, what is stall speed? So if this is your first time tuning into our channel, go ahead and hit that subscribe button in your lower right corner. Check us out on Facebook. We're uploading new content daily. Check out our website. We have our catalog uploaded there. It's hughesperformance.com. Over 1,300 new part numbers for 2019, and we're constantly coming up with new stuff as we go. Thanks for tuning in. So getting right into it, stall speed is the maximum amount of impeller RPM that can be achieved without the turbine physically moving. It's important to note that stall speed is not a fixed number. So if you have a torque converter that has an advertised stall speed rating of 3,000 RPM, that converter is not going to provide 3,000 RPM of stall speed in every possible application that it could be used in. A torque converter is a load-sensitive device, and this is universally true. There are no exceptions to this rule in the automotive industry. A torque converter is going to respond with a varying stall speed number based on the torque output of the engine, the vehicle weight, the gearing in the rear axle, the rear tire diameter, or in the case of a front-wheel drive vehicle, the front tire diameter, gear ratio in the transmission. All of these factors contribute to the maximum amount of stall speed that can be achieved with a torque converter. So that same 3,000 stall speed rating that we're talking about in our example could be put behind your basic 400 horsepower small block engine in a 3,500 pound passenger car with a 3-speed automatic transmission and a 373 rear axle ratio. And it's probably going to provide you right in the neighborhood of 3,000 RPM of max stall speed. You could take that same torque converter, you could put it in a 5,000 pound truck with a big block engine, and again a 3-speed automatic transmission and a 342 rear axle ratio and maybe a 31-inch tall tire. And depending on the torque output of the engine, this same converter that normally has an advertised stall speed rating of 3,000 RPM could potentially provide as much as 4,000 RPM or more of stall speed. So you have a pretty wide window of stall speed that can be achieved with any given torque converter based on the application that it's being used in. Now, stall speed is a little bit of a mixed bag as far as nomenclature goes. Because it's not a fixed rating, there's actually different ways to define stall speed. We commonly refer to 3 different areas when we're talking about stall speed. One, you have foot brake stall speed. That's the amount of stall speed that the torque converter can achieve when you have the brakes fully engaged and you're applying the throttle against the converter without the vehicle providing any forward motion or without overpowering the brake assembly and the wheels turning. Foot brake stall speed is universally going to be lower, sometimes significantly so, than your advertised stall speed rating of any given torque converter. The reason for that is the torque converter is multiplying your engine's output torque. As it's multiplying torque, you're delivering more foot-pounds of torque to the rear axle. You have a ring and pinion that is providing torque multiplication from the gear ratio. So your, say, 400 foot-pounds of torque at 2,000 RPM could be 600 or 800 foot-pounds of torque that's actually trying to be applied to the rear tires. By the time the converter multiplies the torque, that torque is multiplied through the ratio of the transmission, and then further multiplied by the axle ratio in the rear end. As such, you're going to have so much torque at such a low RPM, you're either going to physically override the brake's capabilities of withstanding all that torque, or you're going to override the coefficient of friction that's available between whatever surface you're on and your tires. Consequently, the tires are going to start spinning. Foot brake stall speed has nothing to do with how accurate a converter has been built in terms of function or performance or what stall speed it should be providing. Foot brake stall speed doesn't give you any real relevant data or anything useful in terms of how your converter should be reacting to your combination. If you bought a torque converter that has an advertised stall speed rating of 4,500 RPM and you can only foot brake it to 1800 RPM, that doesn't mean that the converter's built wrong or in any way defective. That typically means that you have an engine that doesn't make a lot of low-speed torque, or you have a lot of ratio between the transmission low gear and the rear axle ratio. And again, that's one of those things that it's just not a good indicator of converter performance or function. So if you're concerned about the amount of foot brake stall speed that you're seeing with your converter, give us a call so that we can talk about your combination and help you understand what's actually going on front to rear in the car, why you're seeing that number. We're ready to talk to you and help explain it so that it all makes sense. You can see that the converter actually is doing its job. The second parameter we discuss when talking about stall speed is flash stall speed. Flash stall speed is the amount of RPM that you can observe when the vehicle's in a rolling condition at a low speed. It's typically easiest to check it in second or third gear. Obviously, you want to do this on a closed course where you're away from other people. You don't want to hurt yourself or others. You don't want to get in trouble with the law by doing this out on the street. But you can be rolling along in your vehicle at a low speed in second or third gear, say 5 to 10 miles per hour, and just quickly transition to wide open throttle while you're observing the tachometer. Wherever you see your tachometer swing up to in terms of RPM reading, that's a good indicator of your flash stall speed. That's a much more useful figure to gauge how the converter's functioning, what type of performance the converter's actually capable of. When we're talking stall speed, we most frequently talk flash stall speed. When we have you on the phone or communicating via email, we're going to want to know that number. The third parameter that you have is static stall speed, and that kind of goes back to the beginning of the video where that's the max amount of RPM the impeller can achieve without the turbine physically moving. And the only way that you're ever truly going to know the absolute max static stall speed of any torque converter is to either have the drive wheels permanently locked so that they physically just can't turn, which is obviously really difficult to do, or to have a trans brake in your transmission. If you have a rev limiter, you're going to have to disable your low speed rev limiter so that you can observe this. You can put the vehicle on the trans brake. You can go to wide open throttle for just a second and observe how much stall speed can be achieved without any rev limiting capabilities, and that's going to give you an accurate idea of the max static stall speed that your converter is capable of. This is also a very useful figure when we're talking converter performance and converter function. So you just want to pay close attention to advertised stall speed ratings and don't make your converter choice based on advertised ratings. Even if you've just got a basic combination, a street rod or a pickup truck, I mean, you could have a tow vehicle, where we do have a shelf stock regular Joe entry-level converter available, it's still worth your time to call us or shoot us an email and get that recommendation so we can help fine-tune your converter selection process. You're spending good hard-earned money to buy our products, you're getting a good quality product. We want to help you achieve the maximum amount of satisfaction with your vehicle and with our products, and to do that we need to know what you're building, what the converter's going in, and we're happy to talk to you so that you get the right product the first time. So what creates stall speed? Well, stall speed is primarily influenced by impeller fin angle, clearances that are set up inside the converter during the converter build, and stator design. What you see here is a variety of components from the General Motors 245 millimeter torque converter family. This is a really common core to use in street performance converter builds, all the way up to high horsepower drag racing converter builds. It's a super versatile core. They're readily available. Pretty much everybody in the industry uses this core for a wide variety of their product offerings. It's very versatile because General Motors produced 6 different impeller options with different vane angles, and as you can see, 5 different stator options with different vane counts and vane angles and vane shapes. So we can tune the 245 core to a very, very broad expanse of vehicles, power outputs, and stall speed requirements. Getting into the actual angles and shapes, you can see in the impellers here that starting with the lowest stall impeller that GM produced in this particular core, You can see the impeller vane is stood fairly straight up in the inner and then transitions to a very positive angle at the outer drive tip. Generally speaking, as we have a straighter vane in this area and a more aggressive bend towards the outer tip, we're going to experience lower and lower stall speeds. We typically experience higher ratios of drive within the converter for improved efficiency as well. As we move into the medium stall impeller compared to the low stall impeller, you can see we're still stood fairly straight up on the inner here, but it has a much less aggressive positive move as it transitions into the outer tip angle. This impeller is going to stall higher than this impeller. Moving through here, we have a more negative angle shape. You can see that the vanes have a bit more negative sweep to them and come up to a more neutral position. Again, that's going to provide a corresponding increase in stall speed. This is basically the same style impeller as this, but GM took the outer tip of the impeller vane and stamped it so it has just a very slight positive sweep. So this particular impeller basically kind of splits the difference between the medium stall and low stall impellers. And then we get into the high stall impellers, and you can see in both of these examples they have progressively more negative impeller fin angles. As we go more negative on the angle, we increase stall speed. The reason for that is the negative angle traps more fluid at the outer tip. Because it traps more fluid at the outer tip, it requires more RPM to get the impeller to flow fluid to the turbine to get the turbine begin moving. If you go back in our first episode, you can see the electric fan example where the powered fan begins turning the unpowered fan. Well, same concept. As we change this angle, we need more centrifugal force pushing that fluid to the turbine to get that turbine or fan to spin. We can also change stall speed with stators. We have the 5 different stators here, and this is just a small example of stators that we have available. Because of our CNC machining options and our fabricated steel stator options, we literally have an innumerable amount of stator options to tune your converter program. Again, we're using the GM245 family here just because it's a really good visual example for a wide variety of OEM options that provide a significant range of stall speed. So we have the 18 vane stator. This stator is commonly referred to as a 681 casting. You have the GM casting number here. This is the lowest stall stator. You can see that it's got a relatively steep pitch to the vanes, pretty wide window area, flows a lot of fluid. 18 vanes, it's got really good torque multiplication characteristics. This is the popular and well-known 082 stator, again based on the casting number. Also an 18 vane stator, but it's got less dramatic vane angle. As we start to roll the stator vane angle over, this is about 50 degree, this is roughly 45 degree. We're closing that window area, so we're increasing resistance to fluid flow through the stator. We therefore see an increase in initial stall speed. This is the 102 stator. This one's kind of rare. This is a factory high stall stator. You can see it's got very little window area, very aggressive, fat, rounded, ramped vane shape. This stator is going to give a lot of stall speed, but it's also not very efficient. Very, very few builds rely on this type of stator, typically really small displacement, high RPM, low torque output applications. We have what's called the 682 stator. This is a 14 vane, big window area. Now normally you'd think this would be a low stall stator because of the big window area between vanes and the low vane count, but it's actually considered a high stall stator because it has a very, very shallow pitch to the vanes. So this stator design and similar models out there to it give very good initial flash characteristics. But because they have a big window area, once that stall speed has been achieved, they start flowing a lot of fluid. They're a very efficient stator. Stators of this type tend to work good in turbo cars where you need to transition into a high RPM and build boost quickly, but then you need a converter to lock up tight. And then finally, you have the 391 stator. Again, this is a little bit of a rare bird in the 245 family. 21 vane, very thin vanes, fairly shallow angle. Again, this is a high stall stator. Flows a lot more fluid than this stator does, so it's going to be more efficient. And with the extra 3 vanes compared to your 18 vane stators, it's going to have more torque multiplication. When it comes to stator design, as we increase vane count, we increase torque multiplication. We have more vanes available, so we have more surface area available, accelerating that fluid back to the impeller, so we're creating more drive force. Because the window area is smaller by the space that's physically taken up by the extra vanes, it also provides more stall speed, again, due to restriction through the stator to fluid flow, just the resistance that's created, so fluid starts flowing efficiently through it. Moving the other way, we can go to lower vane counts on the stator, and we're going to decrease torque multiplication, and we're going to lower stall speed from the bigger window area. Low vane counts are typically necessary in extreme high horsepower combinations. If you get into nitrous cars, big horsepower turbo cars, blower cars, even really large cubic inch, 7, 8, 900 cubic inch plus engines that are naturally aspirated, you're going to see stators used that have lower vane counts and much bigger window areas. One, you have a lot more torque being applied, so you don't need as much torque multiplication provided by the stator. And 2, you're putting more torque to the converter. It's naturally going to stall higher because you have higher input torque, so you have to manage that torque with your impeller vane angle design as well as your stator design. We mentioned clearances when it comes to converter builds. I can take an impeller, I can take a stator, and I can physically increase the clearance between the impeller and stator, and we're basically creating an inefficiency in the converter, an internal fluid leak, so to speak. It's going to increase stall speed. I can also increase clearance between the stator and between the turbine and basically achieve the same thing. Now, I can build a properly clearanced converter where I'm maintaining a good overall efficient operation, but I can go into the stator and I can start to remove material from the impeller side of the vanes. I can open up that window and I can shorten the overall height of the vane, and I'm actually going to tighten the converter because we're reducing resistance to the fluid flow through the stator, and we are lowering the point at which the converter can achieve an efficient fluid coupling. Conversely, I can take this same stator and the same properly clearanced converter, and I can machine the turbine side of the vanes. I can either come in here with a mill and I can create a flat, or I can actually shorten the overall height, and I'm actually increasing stall speed. And the reason for that is it requires more centrifugal force, more RPM, to get that fluid flowing through the stator. Those type of stator modifications are really common in the industry. When you get into CNC machine stators, you don't see as much of that type of machining taking place because we're basically starting clean sheet, and we can make the stator do whatever we want. We can incorporate any vane count, we can incorporate any window area, any pitch angle, and fine-tune the stator right from the get-go without additional machine work. Same holds true in our Pro SSX fabricated steel stators. We're building it from scratch. We can do whatever vane count and vane angle we want. Our Pro SSX stators are typically our most efficient, highest flowing stators. Fantastic choice in any max effort combination. Our Pro Series stuff can be used anywhere from a street car to a top sportsman application, everything in between. So we have a lot of versatility in our custom converter builds. When we get into turbines and how turbines affect stall speed, not really much going on there for the most part. Turbines being the driven element, the element that's turning your input shaft and therefore providing drive to the drive wheels, don't really affect stall speed nearly as much as your impeller vane angles and your stator designs do. We have seen in testing that we can alter this inner vane angle a bit and have some effect on stall speed and coupling characteristics. But to be honest, we just don't have enough good data on it yet to even really justify trying to fine-tune stall characteristics via the turbine. We pretty much just rely on this, and this is true of just about any builder out there, to just be the simple driven element that delivers power to the rear wheels. So that basically is what's going on with stall speed. If you have any questions, you can ask those in the comments below. We'll be happy to interact with you online. You can shoot us an email on hughesperformance.com. We have a tech form you can fill out for a custom converter recommendation or just a general contact form, and we'll get right back to you. You can give us a call at 800-274-RACE, that's R-A-C-E, or send us a private message through our Facebook page and we'll respond immediately. We look forward to talking to you. We have 4 very experienced, very professional sales staff just waiting to talk converters with you and help you make an educated decision. If you have an off-brand converter that you want checked out or stall speed tuned on, we're happy to do that as well. You can ship it to our facility and we'll let you know what we can do. So look forward to our next episode. Be sure to hit that subscribe button and tune in as we continue our converter series.